Okay, just continuing on from the previous video, we can calculate the amount of energy or the quanta of energy that a photon is carrying by using this equation, E equals H times nu. So E is for energy, and that'll be in the unit of joule. And whoops, don't do that. So energy is going to be in joules. And then H is a constant we call Planck's constant. And this is something we would never ask you to memorize. It's on your pink sheet. It is 6.626 times 10 to the negative 4th joule seconds. So really there's like a, 1 second, I'm trying to write. It's the product of joule times second for the unit. And then, like I said, it's also, we have the nu again, which is frequency, and that is going to be in inverse seconds, which are also hertz. So if we do a calculation with this, I'll just show you. If you remember, we did, in the previous set of notes, we calculated the, I can't remember if it was the wavelength of the, oh no, it was frequency. I think we were given the wavelength of the lithium color from the flame test. So we are going to this time calculate the amount of energy of each photon that's emitted from the flame of the lithium. So in the question, you can see that we're given the frequency. And we know Planck's constant. And then we're gonna, our unknown is energy. So this one is just gonna be a straight plug in the numbers. So Planck, and then we're gonna multiply that by the frequency. And I am running out of room here, so let me try to move this over here. And I'll get rid of that. Okay, so we would multiply that by the 4.28 times 10 to the 12th. And I'm going to write the hertz as 1/2 because then you can see the unit cancellation. The seconds cancel and you end up with joule, which makes sense because you are calculating energy and that is the unit for energy. And then, by the way, then when I multiply this out, I get, let me just show you because some of this isn't on the screen. I keep having to move this thing. But there's my work over here. And my answer is, I'm going to give it 3 sig figs because I have 3 up here in my frequency. And 2.84 times 10 to the negative 21st joules. So that would be the amount of energy of a photon of the light emitted when we did the flame test on the lithium. Let's do another one. So sometimes I will give you the wavelength. So in this problem, and then I'm going to let you guys try it while I work it out and pause the video. In this problem, you have the wavelength, and let's just put a decimal there so it has 3 sig figs so it's more normal. So the green copper color that we made in our flame test has a wavelength of 500 nanometers, and we want to know energy. So we are going to have to use the equation, the speed of light equals the wavelength lambda times nu, and solve for frequency. And then we can plug in using Planck's constant to get the energy. So I'll let you guys try that one, and then you can check it if you want to pause the video and then check it in just a second. So here is the work for this problem. We are given the wavelength. So from that and the speed of light, we can calculate the frequency. So I have that on the right side of my, I keep getting in the way. How do I get out of here? You can see that the speed of light is 3 times 10 to the 8th. The wavelength given was 500 point nanometers, and we're looking for the frequency so that we can then use that in the energy equation. So first thing I have to do is convert my distance into meters from nanometers. So I'm using dimensional analysis. You can see that my there's 10 to the 9th nanometers in 1 meter, and then I ran out of room, but I end up getting 5 times 10 to the negative 7th meters, and then I can plug that into our speed of light equation, and we can solve for frequency. So I'm dividing, in order to get frequency by itself, I take the speed of light right here divided by the wavelength. And when I do that, you can see that the meters cancel and I end up with 1/2, which is hertz. I'm going to leave it as 1/2. It doesn't really matter to me though. And then I'm going to take that number and use it in the next part. Ultimately, what I'm trying to do is, I know I want the energy of this photon of light that's being given off, and I'm going to use Planck's constant, and I'm going to use that frequency I just solved for. So then once I know those, I'm just plugging them in. It's the product of the two. So the frequency times Planck's constant ends up being 3.98 times 10 to the negative 19th joules. So I'll zoom out so you can see that we were trying to solve this problem, and I had to do the work on the right before I could use that answer, that frequency at the bottom there, 6.0 10 to the 14th. Then I could plug that in with Planck's constant and solve for energy. So if you have any questions, let me know.